In the quietest part of the night, when the world lowers its voice and thoughts begin to slow, there's a doorway that opens into a stranger, softer universe. A place where light arrives in tiny packets, where a single particle can draw a pattern like a wave, and where empty space is never truly empty at all. Tonight, this journey drifts through quantum riddles, entanglement, and the gentle hum of the vacuum, calm mysteries that feel like science and sound like a lullaby. If you enjoy these slow, immersive stories, please take a second to like the video, subscribe, and turn on notifications so you can find your way back here whenever the night calls. And now, let everything settle as we begin. In a quiet room near the end of the day, a lamp holds a small circle of light. Outside, streets and trees keep their familiar shapes, and everything appears obedient to simple rules. Objects fall when released. Sounds fade when the source is gone. Even moonlight seems steady, as if it never needs to decide what it is. At human scale, the universe feels continuous and reliable. A glass warms gradually in a hand. A kettle sings before it boils. A shadow slides across a wall without breaking into pieces. This calm continuity becomes so normal that it is easy to mistake it for the deepest truth. Yet the deeper truth waits in places that are almost too small to imagine. This journey drifts toward that hidden scale, where matter and light stop behaving like solid certainties and start behaving like questions with weighted answers. Along the way, a few gentle mysteries will be carried from section to section. Why does energy sometimes arrive in counted portions rather than smooth flow? Why does learning which path a particle takes change the pattern it leaves behind? And how does probability become the single definite scene that appears to the senses? For a moment, everything is still. The mind can rest on a simple image, a piece of metal warming in darkness. No drama, only patience. As heat rises, the metal begins to glow, first a faint red, then brighter, edging toward white. This seems ordinary, like embers in a fireplace, but inside that steady glow, classical physics meets a quiet impossibility. In the classical picture, energy is endlessly divisible. A vibrating atom can exchange any amount at all, from an almost nothing to an almost anything, as if nature can always pay with smaller coins. When scientists apply that smooth assumption to the light from hot objects, their equations predict that higher and higher frequencies should carry more and more energy without limit. The result is not merely incorrect, it is absurd, as though a warming coal should pour out infinite power in invisible ultraviolet light. The world refuses to do that. Reality stays finite. Nothing urgent happens here. There is no loud failure, only a mismatch between prediction and observation sitting calmly on the lab bench. And yet this mismatch is a doorway. To step through it, one simple change is enough. Energy does not trade hands in an unbroken stream. It arrives in small packets in discrete steps, so that certain exchanges are allowed and others are not. With that single adjustment, the runaway infinity disappears and the gentle glow makes sense again. A soft curiosity appears at once. If heat and light obey a rule of steps, what else might be stepped as well? Perhaps nature has a smallest grain of action, a minimum unit that cannot be subdivided further. Perhaps the smoothness of everyday life is an illusion created by immense numbers of tiny events piling up too densely to distinguish. Time seems to stretch, the lamp remains steady, and the mind can drift over a second consequence of this new idea. If energy comes in packets, then light itself begins to look less like a continuous wave and more like something that can arrive one piece at a time. That thought will soon meet an experiment where light strikes metal and electrons escape only when the light carries enough energy per packet, no matter how bright the beam becomes. Before that, it helps to hold a gentle distinction. In classical physics, a system is assumed to possess definite properties at every moment, whether anyone checks or not. In quantum physics, the first description is often a landscape of possibilities, a distribution of tendencies. The mathematics does not claim that nature is careless. It claims that at small scales, possibility is part of what nature is. Another curiosity follows quietly behind it. If a particle is described by possibilities, then what does measurement do? Does it simply reveal an answer that already exists? Or does it force one of the possibilities to become real while the others fade? The journey will return to this question when it reaches the double slit, where a single particle behaves as if it explores more than one route until information about its route becomes available. Nothing urgent happens here. The mind can picture a calm river made from countless droplets. Each droplet follows tiny rules, yet together they produce a surface that looks smooth and predictable. In the same way, the definite world of chairs and streets can be a collective calm formed when vast numbers of microscopic events overlap and average into stability. This does not remove mystery, it relocates it. The strangeness lives where single events matter, where one photon, one electron, or one atom is not drowned in a crowd. There, nature seems to hesitate because its rules describe probabilities until an interaction fixes an outcome. The journey will keep returning to that quiet hinge point where possibility becomes fact. For now, the first clear takeaway is simple and comforting. Quantum theory begins with a problem that is gentle and familiar. A warm object glows. Classical reasoning predicts an impossible infinity. The universe resolves the conflict by being granular, where intuition expects smoothness. The world remains stable, but its stability rests on counted exchanges that happen beneath notice like tiny footsteps too small to hear. As the room stays calm, the story slides toward the next scene. A clean metal surface waits in darkness, and light approaches it like a careful test. The next section follows that light and watches how the universe decides with surprising strictness when an electron is allowed to leave. In a laboratory that feels more like a careful workshop than a place of spectacle, a small metal oven warms slowly. The room is dim, not from secrecy but from practicality. Bright light makes faint glows harder to measure. On a bench sits a simple object that becomes strangely important, a hollow cavity, a box with a tiny opening. Its inner walls darkened so that light entering rarely escapes again. From the outside, the opening looks like an eye no larger than a grain of sand. From the inside, it behaves like a trap. Light that slips through bounces again and again, losing itself against the interior until the cavity's glow depends on temperature alone. It is in a useful sense the purest light that heated matter can make. Nothing urgent happens here. Heat rises, atoms jostle, and the cavity fills with steady radiance. Yet in this steadiness, the universe offers a puzzle that refuses the old rules. Classical physics treats the cavity like an orchestra of possible vibrations. Each mode of light in the cavity is expected to share energy in the democratic way thermodynamics suggests, but the number of modes grows as higher and higher frequencies are considered, and the calculation runs away. The mathematics insists that the cavity should pour more and more energy into the high-frequency end without limit. The prediction becomes an infinity. The real glow stays finite. A soft curiosity appears. How can a theory that guides planets and bridges stumble on something as gentle as a warm light? For a moment, everything is still. The spectrum can be pictured as a calm landscape, faint at low frequencies, rising to a rounded peak, then fading again. As temperature increases, the peak slides like a slow tide toward higher frequencies. Experiments draw this curve again and again, and it does not bend to classical expectation. The same quiet signature appears far beyond the laboratory. Sunlight carries it. The glow of a furnace carries it. Even a distant star seen through a spectroscope offers a curve shaped by temperature, as if heat everywhere speaks a common language. Into this scene steps a physicist who does not seek revolution. Max Planck works with a mathematician's patience, treating the glow, not as metaphor but as a problem of fitting. Around the turn of the century, around 1900, the question is not what quantum theory is. The question is why the curve has this shape. Planck tries familiar tools and they fail. At last he introduces an assumption that feels almost like a bookkeeping device. The microscopic emitters in the walls, the oscillators that exchange energy with the field, do not trade energy in any arbitrary amount. They trade it in steps. The size of each step depends on the frequency, like a staircase whose risers become taller for faster vibrations. Once the steps are admitted, the catastrophe dissolves. High-frequency modes no longer receive unlimited energy because exciting them costs too much in a single exchange. Thermal motion in the walls can afford fewer of those costly steps, so the spectrum naturally falls away instead of rising to infinity. Nature in effect refuses to make change below a smallest coin. Nothing urgent happens here. The cavity continues glowing. The equations, however, stop misbehaving. Another gentle hook follows. If energy is quantized in the exchange between matter and light, then energy itself begins to look granular. The smooth ramp of classical thought becomes a staircase. The steps can be tiny, too small to notice when countless exchanges blur together, but at the level of single events the steps matter. Planck introduces a constant to set the scale of those steps, a new marker in nature that quietly separates two worlds. When energies are large compared with that scale, the staircase looks almost like a ramp, and classical physics returns as an excellent approximation. When energies are comparable, the steps can no longer be ignored and intuition must soften. Time seems to stretch. The cavity's light looks continuous to the eye, yet the new idea suggests that continuity is a collective effect, like a smooth surface made from countless grains. The glow is not a single, uninterrupted stream. It is an immense crowd of exchanges, each one counted. There is a calm satisfaction in how modest the change is. No new force is invented. No hidden gears are added. A limit is simply acknowledged and the world becomes sensible again. For a moment everything is still. The opening in the cavity remains a small dark dot and the light that escapes it remains gentle. But the assumption that began as a fitting trick now points toward a larger question. Is the granularity only in matter's ability to exchange energy, or is light itself also made of packets? Planck, cautious, treats the idea as a method. The universe will soon treat it as a clue. The takeaway settles softly. Warm objects do not radiate with infinite fury because nature keeps its accounts in discrete units. The catastrophe is avoided not by patching the old picture but by admitting that at small scales exchange comes in quanta. This is the first firm sign that the microscopic world is not a smooth river, but a field of counted steps. As the cavity continues to glow without urgency, the story drifts toward the next experiment. Light will strike a metal surface, and the metal will respond with a rule that seems even stranger. Brightness will not matter unless each packet carries enough energy. In that quiet insistence, another door will open. In a quiet corner of the laboratory, light behaves like a tool that can be adjusted with simple care. A lamp is dimmed. A filter is changed. A metal plate waits under the beam, clean and still, as if nothing important should happen at all. The experiment is plain in appearance. Light shines on the metal. Under certain conditions, electrons leave the surface and move into space. They can be collected as a faint current, a measured whisper of motion. The setup feels almost ordinary, and yet the result refuses old expectations. Classical physics treats light as a wave spreading energy smoothly across a surface. In that picture, brighter light should deliver more energy. If electrons are to be knocked free, increasing brightness should eventually do the job. But the metal does not respond that way. For a moment, everything is still. The light can be made intensely bright, and yet nothing happens if its frequency is too low. The surface remains quiet. Then with a different color, sometimes even at a faint intensity, electrons begin to emerge immediately, as if the metal recognizes a threshold and does not negotiate them. A soft curiosity rises. Why does brightness fail while color succeeds? Measurements deepen the puzzle. When electrons do emerge, their maximum energy depends not on intensity, but on frequency. Turning up intensity increases how many electrons are released, but not the energy of each one. It is as if the light arrives carrying a rule: more visitors can come, but each visitor carries the same coin. Nothing urgent happens here. The apparatus simply answers in a way that does not match the wave-only picture. The effect becomes one of the clearest signs that the first hint of quanta is not merely a clever trick. In the early years of the new century, Albert Einstein takes the possibility seriously. Light, though it often spreads and interferes like a wave, also arrives in discrete packets, each packet carrying an amount of energy proportional to frequency. Higher frequency means a larger packet. Lower frequency means a smaller one. In this view, intensity is not how strong each packet is. Intensity is how many packets arrive per moment. A bright beam is a dense rain of packets. A dim beam is a sparse drizzle. But a drizzle made of sufficiently energetic packets can still do what a flood of low-energy packets cannot. For a moment, everything is still. One packet meets one electron at the surface. If the packet carries enough energy to overcome the metal's binding, the electron can be freed and the leftover becomes the electron's motion. If the packet is not enough, the electron stays bound. The energy is not accumulated gradually. The exchange is all at once a counted event. A gentle payoff arrives. The threshold frequency is explained below it. No packet has enough energy, no matter how many packets arrive. The immediate emission is explained when a packet does have enough energy. The exchange happens without delay. And the dependence of electron energy on frequency is explained. Higher frequency packets simply carry more energy per packet. The packet is later called a photon, a quantum of light. Years later, this explanation is treated not as a curiosity but as a foundation. The recognition is notable for its calm irony. The prize most often associated with Einstein is not granted for relativity, but for this account of light and electrons. A beam on a metal plate becomes in hindsight one of the clearest turning points of modern physics. Time seems to stretch. The word photon is small and calm, but it carries a profound change. Light is no longer forced into a single identity. It is not only a wave, it is not only a particle. It is described by rules that allow different aspects to appear, depending on how the situation is arranged and what information is collected. A soft hook follows close behind if light behaves this way. What about matter? In atoms, electrons already reveal a wave-like side. They do not travel on neat circular tracks like tiny planets. They form stable patterns, spread out shapes that behave like standing waves, giving atoms their sizes, their chemistry, and their quiet regularity. Nothing urgent happens here. The mind can rest on a slow image, a metal surface under dim blue light releasing a sparse stream of electrons like dust motes drifting from cloth. Each electron is a single event, and yet together they form a current that can be measured and trusted. Another gentle consequence emerges. Because photons deliver energy in packets, there is an unavoidable randomness in timing. Even in a steady beam, the exact moment an electron is freed depends on individual encounters. The world remains stable in the large, but it becomes probabilistic in the small. For a moment, everything is still. The plate does not care about interpretation, it simply obeys the rule that energy arrives in quanta. The shift is in what prediction means: not a precise moment for a single event, but a reliable pattern across many events. The section's calm conclusion is simple. The photoelectric effect reveals that light carries energy in discrete packets whose size depends on frequency. Intensity controls the number of packets, not their individual strength. With that, a stubborn experimental fact becomes understandable, and quantum ideas gain a physical foothold. As the laboratory light dims again, the story drifts toward the next step. If photons can behave as both wave and particle, the next question turns outward. Can particles of matter carry a wavelength of their own? And what does a path mean when even a single electron is described by possibilities? A long hallway in a research building holds its quiet air. At the far end, behind a door that closes softly, a beam of particles travels through a vacuum tube as calmly as a thread of smoke. Nothing about the tube looks dramatic. It is glass and metal seals, and gauges a careful attempt to keep the inside empty enough that a particle can cross without too many interruptions. In the old picture, a particle is a tiny object with a path. It has a position then, another position, and between them a trajectory that could be drawn like a pencil line. Light, meanwhile, is a wave that spreads and interferes. But after the photoelectric effect, the boundary is no longer firm. Light can arrive in packets. It behaves like a wave and like a particle depending on the arrangement. A soft curiosity follows naturally. If waves can behave like particles, can particles behave like waves? For a moment, everything is still. The mind can rest on a simple image, a calm sea at night where waves roll in broad fronts and a single pebble arcs through the air with a definite narrow path. In ordinary life, these are separate kinds of motion. Yet the microscopic world has already shown that it does not feel obligated to match ordinary categories. In the early 20th century, Louis de Broglie proposes a quiet symmetry. If light has both wave-like and particle-like aspects, then matter might also carry a wave-like aspect. Every moving particle in this view is associated with a wavelength. The faster the particle, the shorter the wavelength. The slower the particle, the longer. It is not presented as poetry. It is presented as a rule that would make the strange new physics feel less arbitrary. This suggestion immediately offers a gentle payoff. Inside atoms, electrons do not sit at random distances from the nucleus. They occupy certain stable patterns. Earlier models speak of allowed orbits, but the reason for those allowed states becomes clearer when electrons are treated as waves. A wave can form a stable standing pattern only when it fits neatly around a region like a vibration that closes on itself without tearing. In that sense, the electron's orbit becomes less like a track and more like a shape, an arrangement of wave patterns that can persist. Nothing urgent happens here. An atom remains an atom, quietly holding its structure. But the idea that the electrons have wavelengths makes the stability feel less like a mystery and more like a natural consequence of wave behavior. Another curiosity arrives. If an electron is a wave, can it show wave behavior in the same obvious way that light does through interference and diffraction? A crystal provides a calm answer. Inner solid atoms are arranged in repeating layers like a three-dimensional lattice. When a wave passes through such regular spacing, it can scatter and produce patterns of bright and dark directions, a kind of geometric signature. This is how light reveals the structure of crystals in familiar diffraction experiments. If electrons truly carry wavelengths, an electron beam aimed at a crystal should also produce a diffraction pattern. For a moment, everything is still. In a vacuum tube, electrons leave a heated filament and travel toward a target. They are not seen directly. They are inferred from currents and from impacts on detectors, yet their collective behavior can still leave a pattern like footprints in soft snow. When experiments are performed with sufficient care, electrons do in fact diffract. The scattered intensity forms peaks and valleys in directions that match what wave theory predicts, provided the electron wavelength is chosen correctly. Separate research groups find such evidence in different ways, and the message is consistent matter, under the right conditions, behaves like a wave. This is not the wave of a water surface. It does not push fluid upward and downward. It is a wave of probability, a wave of tendency. Where the wave is large, detection is more likely. Where it is small, detection is less likely. The wave is not a hazy metaphor. It is a practical tool that predicts patterns with reliable accuracy. Time seems to stretch. The mind can picture a wave moving through the vacuum, not as a visible ripple, but as a quiet mathematical shape, a cloud of possibility drifting forward. When the electron is detected, it appears at one place as a single event. The wave does not appear on the screen as a smear. The detections appear as points, tiny marks one by one, and yet across many events the points build the same kind of wave-like pattern. A soft hook forms inside that calm fact. How can a single particle arrive as a point and still participate in a pattern that belongs to waves? Nothing urgent happens here. The answer arrives gradually in the way probability works. A single roll of a die is a point event. Many rolls reveal a distribution. In quantum physics, the distribution is not merely a summary of ignorance, it is built into the description. The wave-like function provides the distribution and repeated events reveal it. This leads to another quiet consequence, one that gently reshapes the idea of a trajectory. If a particle is described by a wave spread out in space, then insisting on an exact position becomes costly. To make a wave sharply localized, many wavelengths must be combined like blending notes to form a short pulse. That combination produces a spread in the particle's momentum, the measure of its motion. The more tightly a particle is confined in position, the less sharply its motion can be defined, and vice versa. For a moment, everything is still. This is not a statement about clumsiness of instruments alone, it is a statement about how waves behave. A sharply pinned down wave cannot also be a single clean wavelength with a single clean momentum. The trade-off is woven into the structure of the description. The calm takeaway settles. The microscopic world does not always permit the simultaneous crispness that everyday intuition expects. It permits predictions, but those predictions often take the form of distributions rather than single rigid paths. Classical certainty emerges when many interactions blur the wave-like spread, making one outcome overwhelmingly likely. At small scales, the spread is visible. As matter waves become a stable idea, the stage is ready for the experiment that makes the strangeness feel most direct. If an electron carries a wavelength, then sending it toward two narrow openings should produce interference just as light does. Yet each detection will still be a single point. The next section returns to that quiet apparatus, two slits, one screen, and watches a single particle behave as if it explores more than one route. In a room where air is kept calm and instruments are arranged with patient precision, a small beam travels toward a barrier. The barrier is plain, a thin sheet with two narrow openings cut into it, parallel and close together. Beyond it, a screen waits in darkness, ready to record whatever arrives. The scene feels almost too simple to carry a deep mystery. This section lingers on that simplicity. Two slits, one screen, a stream of particles or light. The question is gentle and clear. What pattern forms, and why does that pattern change when information about the path becomes available? For a moment, everything is still. The beam is switched on and light passes through the pair of openings. On the screen, the result is not two bright bands as the two openings, two stripes intuition suggests. Instead, a set of alternating bright and dark fringes appears like a soft barcode drawn by invisible waves. Where two wavefronts reinforce one another, brightness grows. Where they cancel, darkness remains. Nothing urgent happens here. This is familiar wave behavior, the same kind of interference that appears on water when ripples cross. The surprise arrives when the experiment is made quieter. The beam is dimmed until it sends single quanta one photon at a time, or one electron at a time so separated that each event happens alone. A particle leaves the source, travels through space and strikes the screen. The screen records a single point. Another particle arrives later and makes another point. The pattern does not appear, As a wave spreading across the screen, it appears as scattered specks. A soft curiosity rises. How can isolated point impacts build a pattern that belongs to waves? As more and more single events accumulate, the answer becomes visible in slow motion. The specks do not remain random. They begin to cluster in bands. Dark regions stay mostly empty. Bright regions fill in. Over time, the familiar interference fringes emerge not as a continuous smear, but as a statistical portrait painted by many discrete arrivals. Time seems to stretch. It becomes possible to think of each particle as carrying something wave-like, not a wave of substance, but a wave of probability amplitude. In the language of quantum theory, the particle is described by a wave function whose spread and phase determine where detections are likely to occur. When there are two open slits, the wave-like description includes two pathways. The amplitudes associated with these pathways add together, and the addition can be constructive in some places and destructive in others. Where the combined amplitude is large, detection is more likely. Where it nearly cancels detection is unlikely. Nothing urgent happens here. The mathematics does not force drama, it simply predicts a distribution. The screen quietly confirms it. A second gentle hook appears. If each particle is detected as a single point, then what does it mean to say it goes through both slits? The experiment does not show a tiny object splitting into two pieces. It shows that the description of the particle between source and detection is not a single classical path. Instead, it is a superposition of possibilities that can interfere with one another as waves do. For a moment, everything is still. The barrier with two slits can be imagined as a fork in a road, and the wave function as a mist that can flow through both openings at once. The mist is not a substance in the ordinary sense. It is a structured set of tendencies. Yet it behaves with the same calm logic that waves follow overlap can strengthen or weaken what is later seen. This is also where the idea of coherence enters softly and without complication. Interference requires that the two contributions maintain a stable relationship, like two musical notes that keep phase with one another. If the source is too chaotic, or if random disturbances scramble the relationship, the fringes blur. The pattern is fragile not because it is unreal, but because interference depends on subtle regularity. A third curiosity follows close behind it. If the fringes come from interference between possibilities, what happens when an attempt is made to learn which slit each particle uses? In practice, the experiment can be modified in many ways. A detector can be placed near each slit, ready to register a passage. A tiny interaction can be arranged so that the particle leaves some mark, some trace that in principle distinguishes the left route from the right. The important feature is not the particular gadget. The important feature is that which path information becomes available to the world. Nothing urgent happens here. The detectors simply sit and wait. But when the information exists, the pattern changes. The interference fringes fade and the screen begins to show what classical intuition expects: two broad regions corresponding to the two openings without the alternating bright and dark structure. For a moment, everything is still. The disappearance of interference can feel like the universe choosing to behave differently when watched. Yet the modern view frames it more gently. When which path information becomes available even in principle, the two pathways stop being able to interfere. The phase relationship that allowed cancellation and reinforcement is effectively lost. The two alternatives behave like distinct histories rather than overlapping possibilities. This loss is often described as a reduction of coherence. The particle becomes entangled with the detector or the environment in such a way that the left and right alternatives are correlated with different states of something else. Once that correlation exists, the two alternatives cannot combine into a single interfering amplitude in the same simple way. The interference is not destroyed by a mystical act of attention, It is washed out by information becoming embedded in the world. Time seems to stretch. A useful image is a delicate pattern drawn in sand at the edge of the sea. As long as the surface remains undisturbed, the pattern is visible. If a soft tide of interactions passes over it, the pattern remains only as a memory of what could have been drawn, not as what is now seen. The takeaway of this section settles quietly. A single particle arrives as a single point, yet its distribution across many events can carry the signature of wave interference. This happens because the quantum description allows superposition of pathways and because probability amplitudes can reinforce or cancel. When which path information becomes available, coherence is lost and interference disappears, leaving a more classical-looking result. The experiment does not ask for belief, it asks for patience. A screen slowly fills with dots, and the dots form a wave-like order until knowledge of the route reshapes what appears. From this point, the journey naturally moves toward the meaning of observation and measurement. The next section follows the detector more closely and explores how the information, not force, becomes the quiet lever that changes the outcome. A detector looks like a simple device, a small piece of hardware placed near a slit waiting to register a passage. It can be a faint flash in a sensor, a tiny electrical pulse, a subtle change in a field. In the calm light of the laboratory, it does not appear powerful enough to rewrite reality. Yet when it is present in the right way, the pattern on the screen changes as surely as if an invisible hand has smoothed the fringes away. This section follows that quiet change. It stays close to a single question: why does interference disappear when which path information becomes available, even when the particle is still detected as a single point? For a moment, everything is still. The two slits remain open. The source continues sending particles one at a time. The screen waits. The only difference is that the setup now contains a way, sometimes an extremely gentle way, to distinguish left from right. A soft curiosity arrives immediately. It is tempting to imagine that the detector kicks the particle, physically disturbing it and ruining the interference. Sometimes in crude experiments, disturbance does play a role. But the deeper lesson is calmer and more subtle interference fades even when the interaction is arranged to be as minimal as possible. What matters is not a shove. What matters is correlation. In quantum terms, the particle does not travel alone. It travels in a web of relationships. When a detector is capable of marking the path, the state of the particle becomes linked to the state of the detector. One alternative, the left path, becomes correlated with one detector state. The other alternative becomes correlated with another. The particle and the detector become entangled, even if only slightly. Nothing urgent happens here. The detector simply exists and correlation quietly forms. A microhook turns the thought gently. If the detector carries information about the path, then the world now contains a record, however faint, of which slit is used. The two alternatives are no longer identical in every respect. They become distinguishable histories, and distinguishable histories do not interfere in the same way. It helps to picture interference as a kind of delicate overlap. Two wave-like contributions can add or cancel only when they can be treated as parts of one coherent story. Once the story splits into left with this record and right with that record, the overlap becomes inaccessible. The fringes fade not because nature is offended by curiosity, but because the setup now embeds the particle's alternatives into different states of the environment. Time seems to stretch. The mind can hold a small image, a pencil sketch traced on the thin paper. If the paper remains clean, the lines can overlap and create intricate patterns. If the paper is pressed onto another surface and leaves a carbon copy, the sketch is no longer only on one sheet. It is now correlated with another record. The sketch still exists, but the conditions for delicate overlap have changed. A second soft curiosity follows. Does any conscious observer matter here? Does the universe wait for awareness? In modern physics, the calm answer is no. The key is not a mind looking. The key is information becoming physically available, becoming recorded in any way that could, in principle, be retrieved. A detector can register a path and store it in a memory chip. A stray photon can scatter and carry the mark away. A nearby molecule can recoil differently depending on the path. In each case, the particle's alternatives become entangled with something outside the particle itself. Nothing urgent happens here. The environment performs countless tiny measurements simply by interacting. This is where decoherence enters as a gentle bridge. In an idealized equation, the wave function evolves smoothly, maintaining superpositions. In the real world, systems are rarely isolated. They exchange tiny amounts of energy and information with surrounding air, radiation, vibrations, and internal degrees of freedom. These interactions spread the phase relationships that make interference visible. The coherent superposition does not necessarily vanish in a dramatic collapse. Instead, it becomes distributed into correlations with countless environmental details, making interference between the alternatives effectively impossible to observe. For a moment, everything is still. The double slit sits in darkness and the screen waits. Around it, the room is full of quiet activity, thermal motion, faint electromagnetic noise, tiny scattering events. Decoherence is this quiet activity becoming relevant. It is the world's tendency to record. A micro-hook rises from this stillness. If decoherence is so common, why is interference ever seen at all? The answer is practical and comforting. Interference appears when a system is carefully protected, cooled, isolated, and controlled, so that the environment does not steal the crucial information. Photons can be guided through vacuum and shielded from stray scatter. Electrons can be sent through evacuated chambers. Atoms can be trapped and cooled. In these conditions, coherence survives long enough to reveal its pattern on the screen. Nothing urgent happens here. The laboratory becomes a place where nature's quietest features can persist a little longer than they usually do. A deeper consequence follows with calm clarity. Measurement in this view is not a mystical boundary, it is a physical process in which a system becomes correlated with something else in a way that makes alternatives distinguishable. The which slit question is not answered by thought alone. It is answered when the world contains a stable record. This framing also reshapes what observation means. In everyday life, observing seems passive. In quantum experiments, observing is always interaction. Sometimes extremely gentle, sometimes strong, but always a coupling that creates information. Time seems to stretch again. The screen's pattern becomes a kind of diary of information. When the setup allows no path record, the diary contains interference fringes, the signature of overlapping alternatives. When the setup allows a path record, the diary contains two broad bands, the signature of distinguishable histories. The section's takeaway settles softly. Interference is not destroyed by human attention, but by information becoming available in the physical world. Detectors, environments, and stray interactions do not merely disturb particles, they entangle with them, turning superposed alternatives into effectively separate branches that do not overlap in observable ways. Decoherence explains why the macroscopic world appears stable and single-valued, while small protected systems can still reveal their wave-like superpositions. As the detector rests beside the slits, another question begins to drift into view. If information changes what appears when, must that information be decided? Must the choice be made before the particle reaches the slits, or can the decision be delayed until after the particle has already passed? The next section follows that quiet twist where timing itself seems to loosen, and the experimental choice arrives late, yet still shapes the story the screen records. A laboratory corridor is quiet at night, and a single experimental table glows with a small constellation of indicator lights. On the table sits an arrangement that looks almost playful in its simplicity. Mirrors, beam splitters, and a path that can be opened or closed with a last-minute adjustment. The entire device feels like a gentle question asked in hardware. This section drifts into that question. When does a quantum system decide what it has done? If a particle can behave like a wave when no path is known, and like a particle when path information exists, does the timing of the decision matter? For a moment, everything is still. A single photon leaves a source and travels toward the first beam splitter. In a convenient modern version of the double-slit idea, an interferometer. The beam splitter acts like a fork, sending the photon into two possible routes. Mirrors guide each route onward, and later the routes may be recombined at a second beam splitter or kept separate. When the second beam splitter is in place, the two routes overlap again and interference appears in the detection statistics. Certain detectors click more often than others, with a pattern that depends on phase. In this arrangement, the photon behaves as though it has travelled both routes in a coherent superposition. When the second beam splitter is removed, the routes do not recombine. Detectors placed at the ends of the two paths can in principle reveal which route is taken. In that arrangement, interference disappears, and the statistics behave as though the photon has followed one route. Nothing urgent happens here. The device simply offers two calm possibilities: recombine the paths or do not recombine them. A soft curiosity arrives when the timing is changed. The choice of whether to include the second beam splitter can be made late, so late that the photon has already passed the first beam splitter and is already travelling along the two routes. In some designs, the choice is made while the photon is in flight with a fast switch. The experimentalist does not decide in advance whether the apparatus will measure interference or path. The apparatus is allowed to decide at the last moment, and yet the statistics still follow the final arrangement. If the paths are recombined, interference appears. If they are not, interference disappears. Time seems to stretch. It can feel as though the later choice reaches backward, telling the photon what it must have been doing earlier. The mind naturally reaches for a story. If interference is seen, then the photon must have taken both routes. If which path is available, then it must have taken one. But the experiment refuses to lock a single classical story into place. Nothing urgent happens here. The calm interpretation is quieter than time travel. In quantum mechanics, what can be said about the system depends on the entire measurement context. The wave function evolves through the device carrying phase information as long as coherence is maintained. Whether that phase information can later produce interference depends on whether the paths are brought into a situation where they can overlap in an indistinguishable way. A microhook emerges. The decision is not a secret moment when the photon privately chooses a route. The decision is a property of the final experimental arrangement of what information becomes available in the world. For a moment, everything is still. The photon's history is not a film reel already developed. It is more like a set of consistent descriptions that can be assigned once the measurement context is fixed. When the interferometer is closed, the appropriate description is an interference-based one. The two routes remain coherent parts of one evolving state. When the interferometer is open, the appropriate description is a path-based one. The routes become in principle distinguishable outcomes. This is the heart of what is often called Wheeler's delayed choice idea. It does not require the claim that the past is changed in the everyday sense. It suggests something subtler in quantum physics. Certain statements about what happened are not meaningful without specifying how the question is asked and what information is physically available at the end. Nothing urgent happens here. The apparatus remains quiet and the detectors click one at a time. Another curiosity follows. Does this mean the universe is undecided until someone looks? The calmer modern view again points to information rather than minds. The delayed choice experiment can be arranged so that the choice is made by a random physical process and the result is the same. The essential feature is not intention. It is the final structure of correlations that the setup allows. Time seems to stretch again. The photon can be pictured as carrying two kinds of potential: the potential to produce an interference pattern if the paths remain coherent and are recombined, and the potential to produce witch path correlations if the paths are left distinguishable. The system does not need to know the future. It simply evolves according to quantum rules, and the outcome statistics reflect the measurement context that actually becomes real. For a moment, everything is still. The phrase "witch path information" can be held gently. It is not necessarily information that is read, but information that can exist as a stable record. When the interferometer is closed, no stable record distinguishes the roots, so interference survives. When the interferometer is open, the roots can leave distinct records, so interference does not appear. A quiet payoff settles in. Delayed choice shows that interference is not a fragile decoration added at the end. It is a consequence of coherence maintained across the whole setup, and it appears only when the final configuration permits the alternatives to remain indistinguishable. The late decision does not force a retroactive mechanical change. It selects which kind of correlation becomes meaningful and observable. Nothing urgent happens here. The experiment's power lies in its gentleness. A final soft hook begins to form leading into the next section. If interference disappears when path information exists, and if delayed choice shows that the timing of the decision can be late, then another question arises. What if path information is created marked in the world and then later removed, not merely ignored but truly erased? Would interference remain lost, or could it return when the record is destroyed?
The lobotomisms.
Laboratory lights stay low. The devices remain patient. The story drifts toward that next quiet twist where information can be written, and then in a sense unwritten. A quiet experiment can feel like a story about ink that can be written and then gently lifted from the page. In a dim room, optical components sit on a table, like still pieces on a board. Crystals, mirrors, thin glass plates that split a beam, detectors that wait without impatience. The arrangement looks delicate, as if it is designed not to force nature, but to invite it to reveal what it already does. This section follows a subtle idea. Interference disappears when witch path information exists, even if no one reads it. Then the question becomes even stranger. If the path information is created, and later that information is truly removed, can interference return? For a moment, everything is still. A single photon approaches the device that can behave like a two-slit experiment in disguise. Instead of slits, there are two possible routes through an interferometer roots that can later be recombined. Without any marking, the familiar result appears. The distribution of detections carries an interference pattern, a quiet rhythm of likelihood and unlikelihood across the screen. Then the marking begins. The roots are labelled in a physical way, often by using polarization, a property of light that can be oriented like the direction of a gentle vibration. One route is marked with one orientation, the other route with a different one. The marks are not loud. They do not push the photon sideways. They simply make the alternatives distinguishable in principle. Nothing urgent happens here. Yet the effect is immediate in the statistics. The interference pattern fades. The screen shows a smoother distribution, as if two overlapping patterns have been placed on top of one another in a way that washes out the fringes. A soft curiosity rises if the marks are so gentle. Why does the wave-like pattern vanish so completely? The calm answer returns to the same hinge point as before: distinguishability. When the two alternatives carry different labels, they stop overlapping as one coherent story. The interference requires that the alternatives remain indistinguishable. Marking makes them distinguishable, so the combined amplitude no longer produces visible fringes. For a moment, everything is still. The photon arrives as a single detection point as always. The difference lies only in the distribution built across many events and in the hidden bookkeeping of information. Now the experiment adds its quiet twist. In many quantum eraser designs, the photon is not alone. It is produced together with a partner in a correlated pair, created in a crystal that converts one photon into two. These paired photons are linked by entanglement so that information about one can be encoded in the other without any physical message traveling between them. One photon travels toward the screen and creates the visible detection pattern. The partner photon travels toward a separate set of detectors that can either preserve the path information or erase it by measuring in a way that makes the labels indistinguishable. Time seems to stretch. The idea of erasing does not mean destroying a physical object. It means arranging the measurements so that in principle the path label cannot be recovered. The mark no longer points reliably to left or right. The world contains no stable record that distinguishes the routes. Nothing urgent happens here. The detectors click quietly one event at a time. A gentle payoff appears, but it arrives with a subtle detail that matters. If all events on the main screen are collected together, without regard to what happens to the partner, photon, the overall distribution still shows no interference. It remains washed out. The universe does not return the fringes on demand as a single obvious picture. The fringes return only when the data are sorted according to the partner's outcomes, when coincidences are considered, when detections on the main screen are paired with specific kinds of detections for the partner photon. In those carefully selected subsets, interference patterns reappear. Often complementary patterns appear. One subset produces fringes, another produces anti-fringes shifted so that together they cancel in the total. For a moment, everything is still. This is a calm lesson in how quantum information behaves. The interference is not a decoration that the universe paints or erases on the screen alone. It is a feature of correlations. When the which path label exists, the interference is not visible in the overall pattern. When the label is erased, the interference can be recovered in the joint statistics that respect the full entangled system. A soft curiosity follows naturally. Does this mean the past is rewritten? The experiment is often described in ways that sound like time is being bent, especially when the partner photon's measurement happens after the first photon has already struck the screen. But the calmer interpretation is that the experiment does not change recorded events. The dots on the screen remain where they are. What changes is which pattern becomes visible when the full set of correlations is taken into account. Nothing urgent happens here. The world remains consistent, but the story the one can tell about the photon's path depends on what information is actually available and how the total system is described. This turns the idea of observation into something even more precise. Observation is not merely looking. It is the creation of records and correlations. A which path mark is a correlation between the route and some physical degree of freedom. An eraser is an arrangement that removes the possibility of reading that correlation as a stable path record. Interference is the signature of alternatives that remain indistinguishable at the level that matters for prediction. Time seems to stretch again. The quantum eraser becomes a quiet demonstration that information is not an abstract add-on. It is a physical ingredient of reality's descriptions, whether a system behaves as if it travels along one route, or as if it remains in a superposition is tied to whether the environment contains a usable record that distinguishes the routes. For a moment, everything is still. The laboratory's dim light, the steady table, the slow patience of repeated events, these become part of the meaning. Quantum phenomena do not demand belief in paradox. They demand careful attention to what is actually measured, what is actually recorded, and what can be known in principle. The takeaway settles softly. When which path information is created, interference disappears. When that information is truly erased, made unavailable as a stable record, interference can be recovered, not as a single global picture, but within the correlations of the full system. The lesson is not that the past is rewritten, but that the visibility of wave-like structure depends on information, and information depends on physical arrangements. As the experiment's logic grows clearer, the journey naturally drifts toward the mathematical line that holds these behaviors together. The next section turns toward the equation that describes how quantum possibilities evolve in time smoothly and quietly before measurement fixes an outcome, the Schrödinger equation. In a quiet office where the air smells faintly of paper and graphite, a chalkboard stands like a dark window. A few lines of symbols sit on it, unhurried, neither dramatic nor decorative. There is no explosion of colour, no cinematic flourish. And yet this compact statement becomes one of the most powerful descriptions ever written about the microscopic world. This section settles around a single idea. Quantum physics needs a rule for how its cloud of possibility changes with time. A wave function, this structured field of tendencies, cannot remain frozen. It shifts, spreads, bends, and interferes even when no measurement is made. The Schrödinger equation becomes the calm law that guides that motion. For a moment, everything is still. The wave function can be imagined as a soft mist over a landscape. Peaks mark where an event is more likely to be found. Valleys mark where it is less likely. The question is not where a particle is as a single point. The question is how this mist evolves while the particle remains unmeasured. A gentle curiosity appears almost immediately. Classical physics uses forces to predict paths. If a planet is pulled, its trajectory curves. In the quantum description, the wave function takes the role of the object being guided. The environment field's boundaries and energies acts like the shape of the landscape over which the mist moves. The Schrödinger equation links the wave function to that landscape and tells how it changes from one moment to the next. Nothing urgent happens here. The equation does not shout, it flows. It is in spirit a rule of continuous change, like the way ripples spread across a pond after a small disturbance. Even when a system is in superposition, when multiple possibilities coexist, the evolution remains smooth and orderly. A microhook hides in that smoothness. If the evolution is so calm and continuous, why do measurements appear to produce sudden outcomes? For a moment, everything is still. The chalkboard remains quiet, and the mind can linger on a simple metaphor in water. A drop enters, then spreads, becoming a soft gradient. This resembles the way a wave function can spread through space. The Schrödinger equation describes that spreading with remarkable precision. It predicts interference patterns, the stability of atoms, and the discreteness of many quantum states without needing to force them by hand. One quiet payoff appears here. Quantization in many cases is not an extra rule glued onto nature. It emerges from the wave-like description meeting constraints. When waves are confined inside an atom, inside a potential well, inside a resonant cavity, only certain standing patterns can persist without tearing themselves apart. Those allowed patterns correspond to specific energies. The world appears stepped because waves must fit. Time seems to stretch. This is why electrons in atoms form stable orbitals rather than spiraling inward like classical charges might. The electron is not treated as a small bead circling on a track. It is treated as a standing wave pattern tied to the atom's structure. The Schrödinger equation predicts these patterns and the energies associated with them, giving chemistry its quiet foundation. Nothing urgent happens here. Salt tastes like salt because electrons in atoms and molecules occupy stable quantum states. The ordinary world rests on that microscopic order. Another soft curiosity follows. How does probability enter? The wave function itself is not a probability. It is more like an amplitude, a structured quantity whose magnitude determines likelihood. When the amplitude is large in a region, detection is more likely there. When it is small, detection is less likely. This is the calm bridge from wave-like evolution to the dot-like events on a screen. For a moment, everything is still. A single electron can be sent toward a detector. The wave function spreads guided by the experimental geometry. Then a single detection occurs at one location. The Schrödinger equation predicts the distribution of such detections across many repetitions, even though it does not specify which single point will appear in a particular run. A micro-hook turns that into a deeper question. If the Schrödinger evolution is continuous and deterministic for the wave function, what exactly causes the single definite outcome? This is the measurement problem, and it sits like a quiet seam in the theory. The equation describes the smooth unfolding of superpositions, yet measurement yields a particular result as though the mist suddenly becomes a single droplet again. Physics offers several ways to speak about this seam, and the journey does not need to choose one as a final truth to appreciate what each is trying to hold. One view treats collapse as an update of information. When a measurement occurs, the description changes because knowledge changes. Another view treats collapse as a real physical process, something that happens objectively under certain conditions. Another view suggests there is no collapse at all. The wave function always evolves smoothly, and what appears as a single outcome is an experience located within one branch of a larger superposition. Nothing urgent happens here. These interpretations disagree about what the wave function is, but they agree on the practical predictions that experiments confirm. The Schrödinger equation remains the engine that evolves quantum possibilities between interactions, and it does so with unmatched success. Time seems to stretch again. It becomes possible to hold two calm facts at once. First, quantum evolution is exquisitely orderly when a system is isolated. Second, the appearance of definite outcomes is tied to measurement and to interaction with larger systems including the environment. A gentle reset line returns. For a moment everything is still. A particle in a carefully shielded trap can remain coherent, its wave function evolving smoothly. The moment it interacts strongly with many degrees of freedom air molecules, thermal vibrations scattered photons, coherence is lost, and outcomes look classical. Decoherence explains how the smooth wave-like description becomes practically unable to display interference, even if the deeper evolution remains continuous. A final payoff settles softly. The Schrödinger equation is not a decorative formula. It is the reason quantum theory can predict interference diffraction tunneling, atomic structure, and the stability of matter with such reliability. It is the quiet melody underneath the strange behavior seen in experiments, and yet it also reveals the theory's most delicate boundary. The transition from evolving possibilities to a single recorded fact. As the chalkboard stays dark and the room remains calm, the story drifts toward the next image, one that makes superposition feel vivid at a larger scale. A closed box, a fragile quantum trigger, and a living system become a symbol not of horror, but of tension between microscopic rules and macroscopic certainty. The next section follows that thought experiment and the gentle bridge called decoherence. And a quiet thought experiment. A simple box becomes a small stage for a famous tension in modern physics. The box is closed and kept as undisturbed as the imagination allows. Inside, a microscopic quantum event is linked to a macroscopic consequence, as if the smallest uncertainty can be amplified into something large enough to notice. Quantum theory treats superposition as ordinary alternatives coexist and can interfere. Yet the everyday world appears stubbornly singular. Tables do not hover between positions, a cup does not appear in two incompatible places at once. The box asks where, if anywhere, superposition truly stops. For a moment, everything is still. The imagined device inside the container is arranged so that a single quantum outcome, such as a transition, a decay, or a yes or no trigger, controls a larger mechanism. If the Schrödinger equation governs the combined system without exception, then the full description should evolve into a superposition of distinct macroscopic alternatives. A soft curiosity rises if the mathematics allows both alternatives. Why does experience insist on one? Nothing urgent happens here. The thought experiment stays gentle and abstract. Its purpose is not to shock, but to refuse a comfortable separation between quantum things and ordinary things. It carries the formal language of superposition across scales until intuition begins to strain. Schrödinger offers a vivid version by imagining a sealed box that contains a living organism linked to a quantum trigger. The image is not a recommendation for action, it is a mirror held up to the theory's words. If the box were perfectly isolated and the quantum rules applied cleanly, the organism would become entangled with the microscopic event in a superposed description. Time seems to stretch. The discomfort can be noticed without turning into dread. The point is the contrast between smooth quantum evolution and the definite records that appear in ordinary life. A microhook appears quietly. When does measurement begin? Is it the moment the lid is opened, or is measurement already happening through unavoidable interactions between the box and its surroundings? For a moment, everything is still. In practice, macroscopic systems are never truly sealed. Air molecules bump and recoil. Thermal vibrations hum through materials. Photons from nearby walls strike surfaces and depart again, carrying away faint traces. Each interaction creates correlation. Each correlation is a tiny record that distinguishes one alternative from another. This is decoherence, the quiet process that makes large-scale superpositions lose their visible wave-like signatures. The wave function can still evolve according to the Schrödinger equation when all degrees of freedom are included, but the phase relationships that enable interference are dispersed into the environment. Information about which alternative leaks outward into countless microscopic details that cannot be gathered back together. Nothing urgent happens here. Decoherence does not by itself explain why one specific outcome is experienced. It explains something slightly different and immensely useful: why interference between macroscopic alternatives becomes practically impossible. It turns an overlapping story into effectively separate branches, like a melody scattered into many faint echoes. A further hook hides inside this idea. The environment does not record every property equally well. Certain features like approximate position leave robust traces because they scatter light and bump air molecules reliably. Delicate phase relations, by contrast, are too subtle to survive. For a moment, everything is still. A dust grain drifting through a sunbeam is struck by photons warmed by infrared radiation and jostled by air. Each interaction nudges the environment into a slightly different state. Over time, the dust grain becomes correlated with countless details and alternatives that differ in position, stop interfering. The pointer states that remain are the ones the environment copies most effectively. A soft curiosity follows if decoherence mainly hides interference. Why does the world feel so decisively single? The deeper measurement problem remains an open seam in interpretation. Yet decoherence provides a soothing bridge from quantum rules to classical appearance. It shows why everyday objects acquire stable, persistent properties and why the imagined box cannot protect coherence for long. For a moment, everything is still. Even if no lid is lifted, the box radiates heat and exchanges photons with its surroundings. Its internal state leaves fingerprints in the environment almost immediately. In a warm room, coherence between macroscopic alternatives would vanish extremely quickly, long before any deliberate inspection. Time seems to stretch again. In carefully controlled laboratories, researchers push against this fragility, not with organisms but with systems that can be cooled, shielded, and simplified. Superconducting circuits rest in ultra-cold refrigerators. Large molecules travel through interferometers under high vacuum. Tiny resonators are isolated from vibration. In these conditions, coherence can survive long enough to reveal interference that would otherwise be lost. Nothing urgent happens here. The experiments proceed slowly and patiently. Their calm lesson is that the boundary between quantum and classical is not a rigid wall. It is more like a shoreline shifting with temperature isolation and the density of environmental connections. For a moment, everything is still. The box becomes less a paradox and more a signpost. It points toward the central role of entanglement and information. It suggests that measurement is a spreading chain of correlations from a quantum event to a detector from a detector to a room from a room into the wider world. The takeaway settles softly. Superposition is not reserved for the tiny, but its visible signatures depend on coherence, and coherence is fragile in a universe that constantly records. From here, the journey naturally drifts toward the phenomenon, where entanglement is not a side effect, but the main structure, where distant particles share one description and correlation becomes a quiet, reliable rule. In a quiet laboratory where light is guided through crystals and narrow fibers, two particles are born together from a single event. They separate almost immediately, drifting into different directions, and soon the distance between them grows large enough that no ordinary influence should pass between them in time. This section rests on a phenomenon that feels like a gentle challenge to distance itself: quantum entanglement. It is not a hidden wire, it is a precise correlation written into a shared quantum state, linking measurements on two separated systems in a way classical stories struggle to imitate. For a moment, everything is still. A detector waits on one side of the room, another waits far away, sometimes across open air. Each measures a property such as polarization for photons or spin for electrons, choosing one measurement direction or another. The surprising feature is not that results sometimes match. The surprise is that the overall pattern can be stronger than any simple local explanation seems to allow. A soft curiosity arrives: how can two distant outcomes remain linked without a message travelling between them? In the quantum description, the pair is not two fully independent objects carrying separate lists of properties. The pair is one combined system with two parts. The shared state does not assign definite values to each particle separately. Instead, it assigns a definite relationship between them. When one side is measured, the joint description updates and the other side's possible outcomes become constrained to remain consistent with the shared state. Nothing urgent happens here. The detectors simply click. The mystery lives in the bookkeeping of the whole. An everyday comparison offers a foothold even if it is incomplete. Two gloves sealed into two boxes are correlated. Opening one reveals what the other must be. But in that story, each glove is already fixed. In entanglement, the relationship is fixed, while the individual outcomes are not assigned in the same definite way before measurement. Time seems to stretch. This is where Einstein becomes uneasy. In 1935, together with Boris Podolsky and Nathan Rosen, he argues that quantum mechanics might be incomplete. Perhaps hidden variables exist beneath the wave function, quietly assigning results in advance, so that correlations can be explained without any non-local feature. For a moment, everything is still. The debate remains suspended between two tastes for explanation, one that accepts probability as fundamental and one that suspects an unseen layer. Then, in the 1960s, John Bell finds a way to turn this tension into an experimental test. He derives inequalities that any theory based on local hidden variables must satisfy. Quantum mechanics predicts that entangled systems can violate those inequalities. The question becomes one that experiments can settle not by persuasion but by statistics. Nothing urgent happens here. A source produces many entangled pairs. Detectors choose measurement settings. Results are recorded and later compared. In careful experiments, the correlations cross the boundary that local hidden variable theories cannot cross. The inequalities are violated. Nature follows the quantum prediction. Over later decades, experiments become cleaner and more distant. Measurement settings are chosen in ways designed to be independent of the source, and the particles are separated so widely that ordinary signals cannot coordinate them in time. The result remains the same. Entanglement persists as a stable feature of nature, even as engineers learn to distribute it through fibers, free space, and carefully timed links. A micro hook follows if the correlations appear instantly. Does this break the limit that nothing carries information faster than light? The quiet resolution is subtle. Entanglement does not provide a controllable faster than light signal. Each local outcome still looks random when viewed alone. No one can choose a specific outcome at one detector in order to force a chosen outcome at the other. Only when the two result lists are later compared does the structured correlation appear. The connection is real in the joint pattern, not in a message that can be sent on demand. For a moment, everything is still. The link is not a beam travelling through space. It is a shared state spanning both locations, a description in which relation can be more fundamental than separate properties. Time seems to stretch again. The consequence is not that causality dissolves. The consequence is that the world is not fully describable as independent local facts carried along independent trajectories. At least some features of reality are relational at the deepest level, and entanglement is the name for that deep relation. Another soft curiosity arrives: can such a delicate connection be used for anything practical? The answer is yes. Quantum cryptography can use entanglement to detect eavesdropping because copying or measuring in transit leaves a statistical scar. Quantum computing aims to preserve entanglement long enough to let interference and correlation steer certain calculations in ways classical machines struggle to mimic efficiently. Nothing urgent happens here. The obstacle is fragility. Decoherence, the same quiet process that makes the everyday world look classical, also breaks entanglement. Cooling, shielding, and error correction become forms of patience, ways of keeping a web of relations from unraveling too quickly. The takeaway settles softly. Entanglement shows that two systems can share a single quantum description across distance, producing correlations stronger than any local hidden variable story can reproduce. It does not create a faster-than-light telephone, but it does reveal that relationships can be fundamental ingredients of reality. From here, the journey drifts toward the next landscape, the quantum vacuum, which appears empty, yet hums with fluctuations that can leave measurable traces. In the deep quiet between stars, space looks empty. A telescope points into darkness and finds no glowing gas, no dust clouds, no obvious light. In the language of everyday life, this seems like nothing at all. An absence, a pause, a blank page. Yet in quantum physics, emptiness is rarely silent. The vacuum is not a dead void. It is a restless baseline, a lowest energy state that still contains motion of a subtle kind, as if the universe refuses perfect stillness, even when everything visible is removed. For a moment, everything is still. The mind can picture a perfectly dark room with all lamps off and all sounds gone, a kind of ideal quiet. Classical intuition would call this true emptiness. Quantum theory calls it the ground state, and it assigns to it a faint, unavoidable trembling. A soft curiosity arrives: how can nothing contain activity? One gentle path to the answer begins with uncertainty. In quantum mechanics, certain pairs of quantities cannot both be pinned down with unlimited precision at the same time. Energy and time form one such relationship in a practical sense. A system cannot remain perfectly fixed in energy for an arbitrarily short interval without consequence. The ground state is the lowest allowed energy, but it is not a rigid frozen point. It retains what is often called zero-point energy, the minimum vibration that cannot be removed. Nothing urgent happens here. The vacuum does not erupt. It simply carries fluctuations, brief tiny variations like ripples that never quite disappear from a pond. These fluctuations are often described with the language of fields. Modern physics treats light and other forces as fields spread through space and particles as excitations of those fields. Even when no real particles are present, the fields remain, and their ground state includes a constant subtle jitter. In calculations, this jitter can be pictured as pairs of virtual particles appearing and disappearing too quickly to be observed directly as free objects. The word virtual can sound unreal, but their effects are not. Time seems to stretch. A calm example comes from an effect that feels almost like a whisper turned into pressure, the Casimir effect. Imagine two very smooth, uncharged metal plates placed extremely close to one another in vacuum held parallel like two quiet mirrors facing each other. Classical reasoning expects nothing special. No magnets, no static charge, no flowing current. And yet when the plates are close enough, they experience an attraction. For a moment, everything is still. The plates simply sit, and the force between them is small but measurable. It does not come from something pushing in the usual way. It comes from what the vacuum allows to exist between the plates. The space between plates can only support certain field modes, certain standing wave patterns that fit the gap. Outside the plates, many more modes are allowed. The vacuum's restless baseline when constrained becomes slightly different in the narrow gap than in the open region outside. The difference behaves like a pressure imbalance, gently pushing the plates toward each other. A soft curiosity follows. How can a restriction create a force? The answer is quiet and structural. The vacuum is not merely emptiness, it's a state with energy tied to the allowed patterns of fields. Change the allowed patterns and the baseline energy changes. A system tends to move toward configurations of lower energy, and in this case the configuration corresponds to plates being drawn together. Nothing urgent happens here. The force is delicate, and it appears only when distances are extremely small and surfaces are controlled with care. Yet it is enough to demonstrate a strange truth: the vacuum has physical consequences. Another micro-hook rises naturally. If vacuum fluctuations are real enough to move plates, do they affect other systems as well? They do. In atomic physics, certain energy levels shift slightly compared to older predictions because the electron and the electromagnetic field interact with the vacuum's fluctuations. These shifts are subtle, but they can be measured with extraordinary precision. The vacuum in this sense becomes part of the atom's environment even when no external radiation is present. For a moment, everything is still. An atom in darkness is not isolated from everything. It remains immersed in the ground state of the electromagnetic field. The vacuum becomes a background that quietly edits the details. Time seems to stretch again. The same idea drifts outward toward cosmology, where the vacuum's energy becomes one of the most puzzling quantities in modern science. In the large-scale universe, an energy associated with empty space can act like a kind of gentle pressure. Observations suggest that the expansion of the universe accelerates, as if space itself contains a component that does not dilute away as the universe grows. This component is often called dark energy. Some theoretical language connects dark energy to vacuum energy, though. The precise relationship remains uncertain and famously difficult. Nothing urgent happens here. The universe continues expanding at its calm pace, but the existence of an accelerating trend hints that empty space may carry an active role in the fate of everything. A soft curiosity appears in the gap between theory and observation. When physicists calculate the vacuum energy using straightforward quantum field estimates, the result can be wildly larger than what cosmological measurements indicate. The mismatch becomes one of the deepest unsolved tensions in physics. The vacuum is evidently not zero yet. It is not the enormous value simple reasoning might suggest. Something about how vacuum energy gravitates, or how it is defined, or how different contributions cancel remains hidden. For a moment, everything is still. This is not a failure of measurement alone. It is a clue that the vacuum is more subtle than a single number. The calm takeaway settles in layers. First, the vacuum is not the absence of everything. It is a structured ground state with unavoidable fluctuations. Second, those fluctuations can be revealed through real forces like the Casimir effect and through tiny shifts in atomic behavior. Third, at cosmic scales, energy associated with empty space may shape the expansion of the universe, even though its true value and origin remain mysterious. As the mind rests on the idea of an active emptiness, the journey begins to drift toward a darker edge where vacuum fluctuations meet gravity in an extreme way. Near a black hole's horizon, the boundary between inside and outside becomes a stage where the vacuum's jitter can be turned into real radiation. The next section follows that quiet boundary and the question it raises about information. Far from city lights, a telescope dome opens under a steady night sky. The air is cold and still, and the stars look like quiet points pinned to a velvet depth. Among those points, some regions hold a darkness that is not merely shadow. It is a black hole, a place where gravity curves space-time so strongly that escape paths close. At first glance, a black hole seems like perfect silence. Light falls in and does not return. Matter crosses a boundary and vanishes from view. Yet quantum physics rarely permits perfect quiet. Even at the edge of darkness, the vacuum keeps a faint unrest. For a moment, everything is still. A black hole is pictured as geometry, a smooth curvature of space-time and a horizon, marking the point of no return. The horizon is not a wall made of substance. It is a boundary in what paths are possible. A soft curiosity settles in. If the horizon is only a boundary of paths, how can a black hole have temperature or glow at all? The answer begins with the quantum vacuum. Empty space is a lowest energy state that still carries fluctuations. Brief paired excitations can appear and disappear. Near a horizon, curved spacetime changes the accounting and the two partners do not always share the same fate. Time seems to stretch. One partner can drift outward while the other drifts inward. If the inward partner crosses the horizon, it cannot return. The outward partner can escape and behave like a real particle. To a distant observer, the black hole appears to emit a faint thermal radiation. Nothing urgent happens here. For large black holes, the radiation is extraordinarily weak, far colder than the surrounding universe. It is a whisper, not a blaze. Yet the implication is deep black holes are not completely black. They possess a temperature and can lose energy. This idea, developed in the 1970s by Stephen Hawking, ties gravity, quantum fields and thermodynamics into one quiet knot. A micro hook rises from that knot. If a black hole radiates, then its mass slowly decreases. Given enough time, a black hole can evaporate. For a moment, everything is still. Evaporation can be held as a patient leaking away of energy. For stellar mass black holes, the timescales are so enormous that the process is effectively invisible on human horizons. Another thread enters from Jacob Bekenstein. He argues that black holes must have an entropy because thermodynamics forbids simply erasing disorder from the universe. If heat and matter fall in, the total accounting must still work. The surprising result is that black hole entropy scales with the area of the horizon, not with the volume inside. A boundary behaves as if it stores an immense count of possible microstates. Time seems to stretch again. The area law feels like a clue. It hints that with gravity present, information about a region may be recorded on surfaces rather than distributed through volumes. Nothing urgent happens here. The black hole remains dark, yet it begins to look like a thermodynamic object with rules, temperature, entropy, and slow radiation. And those rules lead to a question that becomes one of the most famous in modern physics. A microhook forms quietly. If a black hole evaporates, what happens to the information about what fell in? Quantum theory strongly suggests that ordinary evolution does not destroy information. Details can become scrambled and hard to recover, but they are not supposed to vanish completely. If a black hole fades into radiation, the final radiation should in principle still carry the information perhaps hidden in subtle correlations. If it does not, the mathematical structure that preserves quantum probabilities is threatened. For a moment, everything is still. This is the black hole information problem. It is not a question of human memory. It is a question of whether the universe can lose microscopic distinctions forever. Several proposals answer in different ways. One broad idea is that information is encoded in correlations among the outgoing quanta spread so widely that recovery is practically impossible but not fundamentally forbidden. Another is that the horizon itself carries the needed degrees of freedom so that what falls in is effectively stored on the boundary and later influences the radiation. Time seems to stretch. From these hints grows the holographic principle, the suggestion that the physics of a gravitational region can be described by information living on a boundary with one fewer dimension. Black holes motivate this because their entropy already follows an area rule. The inside may be reconstructible from boundary information rather than being an independent container. Nothing urgent happens here. The principle does not make the universe unreal. It proposes a different way of keeping the books. For a moment, everything is still. The night sky holds the black hole as a quiet absence among stars. Yet that absence is structured. It has temperature. It has entropy. It links geometry to information. The takeaway settles softly. Vacuum fluctuations near a horizon can become escaping radiation, making black holes slow emitters of heat. The horizon carries an entropy proportional to its area, hinting that information may be encoded on boundaries. And the effort to explain evaporation without losing information points towards a tighter link between spacetime and quantum information than classical intuition expects. As faint radiation drifts outward into the cold, the story leans toward its next horizon. If information and geometry are so tightly braided at black holes, perhaps spacetime itself is not primary. Perhaps it emerges from patterns of entanglement like a fabric woven from relationships. In a quiet seminar room, long after the day's conversations fade, a few lines remain on a whiteboard. They are not measurements or data, but sketches, a curved surface, a grid of points, and a web of lines connecting them. The drawings look like separate ideas, yet they point toward a single possibility that modern physics returns to again and again. This section lingers on that possibility: space. Time may not be the deepest stage on which physics plays out. It may be something that emerges gradually and quietly from patterns of quantum information, especially from entanglement. For a moment, everything is still. A familiar image can be held, a sheet of fabric stretched tight. In everyday explanations, mass makes a dent in the sheet, and objects follow the curved shape. That picture belongs to relativity, where geometry is primary and matter responds to it. Quantum theory, by contrast, begins with probabilities and relationships where entanglement ties systems together even when distance grows. A soft curiosity rises if black holes hint that information lives on surfaces, and entanglement ties distant systems into one description. Could geometry itself be a consequence of how information is shared? Nothing urgent happens here. The idea does not require fireworks. It grows from careful consistency. Black hole entropy scales with area. Quantum theory resists the destruction of information, and entanglement appears as a fundamental kind of structure, not a rare trick. One of the most influential hints arrives from a powerful mathematical correspondence proposed by Juan Maldacena in the late 1990s. In simplified terms, it suggests that a theory with gravity living in a higher dimensional region can be fully described by a theory without gravity living on that region's boundary. The boundary theory behaves like an ordinary quantum field theory. The bulk theory behaves like a gravitational space-time. Two different languages describe the same physics. Time seems to stretch. This correspondence can be held as a calm metaphor, a three-dimensional scene represented fully by information on a two-dimensional screen. The scene is not fake, it is simply encoded differently. The surprising part is that geometry and gravity in the bulk can be reconstructed from quantum properties, especially entanglement on the boundary. A microhook appears here. If the boundary theory carries only quantum fields and information what in that boundary, data determines the shape of the bulk space-time. For a moment, everything is still. The answer points repeatedly to entanglement. In many studies, when entanglement between regions of the boundary is strong, the bulk geometry connecting the corresponding regions appears smooth and well-stitched. When entanglement is reduced, the bulk connection weakens. In certain idealized models, removing entanglement can make the bulk effectively pinch or separate, as if connectivity is an emergent consequence of shared quantum structure. Nothing urgent happens here. The claim is not that space-time is built from a literal thread. The claim is that the mathematical features that define distance and connection can arise from patterns of correlation. A second gentle path into the same idea comes from tensor networks, which are methods for describing complex quantum states using webs of smaller pieces. On paper, they look like constellations of nodes joined by lines. Each line represents a shared structure, often entanglement between parts of the system. When such networks are arranged in certain layered ways, their geometry resembles a kind of space. Distances in the network can behave like effective distances in an emergent bulk. For a moment, everything is still. A network diagram can be pictured as a quiet city map at night, where intersections are nodes and roads are links. The map is not the city, yet it carries structure. In these models, the roads of entanglement help determine how far apart regions feel, not in ordinary meters, but in the effective geometry that emerges from the quantum state. A soft curiosity follows. Does this mean that space is at root, a measure of how information is connected? The idea is bold, but it remains grounded in repeated hints. Entanglement entropy behaves like a kind of boundary between regions of a quantum system. In gravitational contexts, related quantities behave like areas of surfaces in space-time. The recurring appearance of area entropy and correlation suggests a quiet unity geometry, and information may be two expressions of the same accounting. Nothing urgent happens here. The theory does not yet stand as a final map of reality. It stands as a converging set of clues. A third microhook appears when entanglement is connected to wormholes. In relativity, wormholes are solutions that connect distant regions through a geometric bridge. In quantum theory, entangled pairs show correlations that ignore ordinary separation. A modern conjecture proposes that these two ideas may be linked. Entanglement and wormhole-like connectivity might be different faces of a deeper structure. For a moment, everything is still. Two entangled black holes can be imagined not as objects for travel, but as a mathematical setup. Their shared state can be described as deeply entangled. In some models, that shared entanglement corresponds to a smooth geometric connection between them, like an interior bridge. The phrase often used for this link is that entanglement and Einstein-Rosen bridges may be connected in principle not as a mechanism for sending messages, but as an equivalence between correlation structure and geometry. Time seems to stretch. The calm point remains. Even if no signal travels faster than light, the global structure of a quantum state can still behave as if connectivity exists at a deeper level than ordinary distance. Nothing urgent happens here. The conjecture does not claim that entangled particles open tunnels for travel. It suggests that when gravity is included, the mathematics that describes entanglement can resemble the mathematics that describes geometric connection. A restful reset line returns. For a moment, everything is still. A diagram of nodes and lines rests on a board, silent and incomplete, yet it offers a soothing shift in perspective. The universe can be seen not only as objects moving through space, but as relationships that, when organized in certain ways, produce the experience of space itself. The takeaway settles softly. Black holes teach that information and geometry are intertwined. Entanglement teaches that correlation can be fundamental. Holographic correspondences suggest that a gravitational spacetime can be encoded by a non-gravitational quantum system. Tensor networks hint that geometry can be reconstructed from entanglement patterns. Together, these ideas suggest a quiet possibility: spacetime may be an emergent fabric woven from quantum information. As the diagrams remain still and the night outside stays calm, the journey drifts toward its final main section. The last step looks forward, not toward loud predictions, but toward gentle frontiers. Quantum technology's new measurements of spacetime's texture and the ongoing attempt to understand dark components of the cosmos through the language of information and fields. In a room cooled to temperatures that feel almost unreal, a metal cylinder rests inside layers of shielding. Thick cables descend into the cold like roots into deep soil. At the surface, the laboratory is ordinary benches, monitors, dim indicator lights. But deep inside the refrigerator, where thermal motion is slowed to a whisper, quantum behavior lasts a little longer than it usually can. This section looks toward what comes next, not as a loud prediction, but as calm frontiers. Quantum physics becomes a craft protecting coherence, distributing entanglement, and turning fragile correlations into tools for understanding matter and the cosmos. For a moment, everything is still. A qubit rests in a circuit balanced between alternatives the way a note can hover between two harmonics. In principle, many qubits can share entanglement linking possibilities into one larger structure. In practice, the environment is always nearby and coherence always has a limit. A soft curiosity rises: what makes a quantum computer different from a classical one? The difference is not simply speed, it is the way interference can be guided. In certain tasks, quantum evolution can amplify useful answers and suppress the rest, as though wrong pathways cancel while right pathways reinforce. This does not help every problem, and it does not replace ordinary machines. It offers a different kind of exploration, most valuable when correlations are central and the space of possibilities grows too quickly for classical tracking. Nothing urgent happens here. Engineers build platforms that behave like careful instruments, superconducting circuits, trapped ions, and ordered arrays of atoms. Each approach has its own strengths and its own noise, but each faces the same quiet opponent error. For a moment, everything is still. A quantum state cannot be copied freely, so protection cannot rely on simple duplication. Instead, quantum error correction spreads information across many physical qubits so that local noise can be detected and repaired without revealing the protected state. It is like hiding a melody in a choir, so the loss of a few voices does not erase the song. A gentle question follows: if many qubits are needed to protect one, how can large machines ever be built? Progress arrives in steps. Control improves, errors fall, and devices grow. Even before full fault-tolerance, quantum processors can already act as laboratories for simulating molecules and materials where classical computation struggles because the state space expands too quickly. Here, the machine is not asked to outthink nature. It is asked to imitate nature in its own native language. Nothing urgent happens here. A molecule becomes a pattern of entanglement and interference, and the processor becomes a mirror that reflects that pattern into measurable outcomes. For a moment, everything is still. Another frontier travels along fibers and through open sky quantum communication. Entanglement can distribute secret keys whose security rests on physical principles because interception leaves detectable disturbance. Beyond key sharing, researchers aim for networks that store and swap entanglement, linking distant nodes without needing to copy unknown states. A soft curiosity rises: why is distance such a challenge? Because photons are lost, and ordinary amplification relies on copying. So long links must be stitched from shorter ones using quantum repeaters that combine entanglement swapping with memory. It is like building a bridge from many small spans, each one aligned with care. Nothing urgent happens here. Prototypes appear city by city and the work remains patient. For a moment, everything is still. A third frontier is quieter quantum sensing. Atomic clocks measure time so steadily that tiny gravitational differences appear as slight shifts in ticking. Matter wave interferometers measure acceleration and rotation. Quantum spins sense faint magnetic fields. In each case, fragility becomes sensitivity, and sensitivity becomes knowledge. A gentle question follows: what can such instruments reveal about the cosmos? Some searches for dark matter already use quantum methods. Certain candidates might appear as extremely faint coherent backgrounds, nudging resonance systems or shifting frequencies by minute amounts. Cavities, superconducting circuits, and networks of clocks can be tuned to listen for these whispers. Even the absence of a signal becomes information narrowing what remains possible. For a moment, everything is still. Dark energy and the vacuum remain open questions as well. Quantum theory suggests a baseline energy to empty space, while cosmology observes an accelerating expansion. The mismatch between simple estimates and measured reality is a deep tension. Future observations and laboratory tests may not solve it in a single leap, but they can steadily carve away uncertainty. Time seems to stretch. Another gentle frontier lies in probing space-time itself. If quantum gravity leaves subtle imprints, tiny fluctuations, unexpected correlations, faint limits to locality, then exquisitely sensitive interferometers and entanglement-based probes might one day hint at them. Even a null result matters because it trims away imagined possibilities and strengthens the quiet confidence in what remains. In this way, progress can look like silence becoming more informative. Nothing urgent happens here. The future of quantum physics looks less like a sudden revelation and more like a long night of careful listening where new tools extend perception into regimes once unreachable. The takeaway settles softly. Superposition, interference, and entanglement move from philosophical puzzles to practical craft. As quantum devices become more controlled, they enable computation and communication, and they also become instruments for asking deeper questions about matter, vacuum gravity, and the dark components of the universe. From here, the journey drifts away from hardware and returns to a quieter view, what it means for a small civilization on a calm planet to keep asking questions. Night remains steady above a quiet planet. Cities' dim oceans keep their slow motion, and the sky holds its distant lights without urgency. Somewhere a person rests, while the universe continues doing what it always does, evolving, interacting, recording faint traces and weaving relationships across scales too large to picture at once. For a moment, everything is still. The journey that began with a warm metal glowing and a puzzling threshold in light ends in a softer place. Quanta appear not as hard answers, but as a gentle way of seeing. Light arrives in packets. Matter carries wavelengths. A single particle paints an interference pattern one point at a time. Information once available reshapes what can be observed. Entanglement links what seems separate. Even emptiness hums with a quiet baseline that can push on metal plates and brighten the edge of a black hole. Time seems to stretch. The strangest part is not that the universe behaves oddly, but that it behaves consistently, in ways that require new intuitions. The microscopic world is not chaos. It is a different kind of order, one in which possibilities evolve smoothly until the world contains a record and where relationships can be more fundamental than isolated facts. Nothing urgent happens here. The mind does not need to hold every detail. The images can soften two slits in a barrier. dots gathering into stripes, a detector that changes a pattern by storing a trace, a vacuum that is not empty, a horizon that glows faintly, a web of entanglement that hints at geometry. In this calm perspective, uncertainty becomes less like a flaw and more like a texture. The universe is not refusing to be known. It is offering knowledge in the form it naturally takes: patterns, probabilities, and correlations that reveal themselves over time. The night continues, the planet turns, the sky remains wide and quiet. And within that quiet, the universe keeps its gentle conversation whether anyone is awake to notice it or not.